Electromagnetic imaging is an ill-posed inverse problem whose solution is usually computationally expensive. Nonlinearity comes from complex interactions between the measured EM field and the material parameters. The ill-posedness arises from multiple scatterings, insufficient measurements, and noise corruption. Due to multiple scatterings of EM waves, a slight variation of targets may change the EM field substantially. In most cases, we only transmitting antenna receiving antenna measurement record the field at specific locations, i.e., the field samples are sparse in space. The attenuation of EM fields caused by diffraction and absorption of media, as well as a noisy environment, further increases the ill-posedness. Solving EM imaging problems often requires accurate modeling of EM wave propagation in the DOI. This process is called forward modeling and is implemented by numerical algorithms such as the finite element method. However, it is computationally intensive, especially for large DOIs. Machine learning, ML, techniques and especially deep learning, DL, show potential in fast and accurate imaging. However, the high performance of purely data-driven approaches relies on constructing a training set that is statistically consistent with practical scenarios, which is often not possible in EM imaging tasks. Consequently, generalizability becomes a major concern. On the other hand, physical principles underlie EM phenomena and provide baselines for current imaging techniques. To benefit from prior knowledge in big data and the theoretical constraint of physical laws, physics-embedded ML methods for EM imaging have become the focus of a large body of recent work. This video surveys various schemes to incorporate physics in learning-based EM imaging. We first introduce background on EM imaging and basic formulations of the inverse problem. We then focus on different types of strategies combining physics and ML for linear and nonlinear imaging and discuss their advantages and limitations. Our aim is to facilitate the study of intelligent EM imaging methods that will be efficient, interpretable, and controllable. In this slide, we explore machine learning, ML, and deep learning solutions for addressing the inverse electromagnetic, EM, scattering problem, which involves retrieving the permittivity of dielectric scatterers from measured scattering data. In electromagnetic imaging, particularly for brain imaging, the problem is often approached as a combination of source and scattering problems. This problem involves determining the permittivity epsilon of dielectric scatterers from the measured scattering data. Electromagnetic brain imaging devices use multiple antennas to transmit and receive high-frequency electromagnetic waves into the brain, which interact with brain tissues, and the scattered field will be received in antenna. These interactions cause scattering due to differences in the tissue's electromagnetic properties. In scattering theory, the problem is described by the Lippmann-Schwinger integral equation, which relates the total field to the incident and scattered fields. The scattered field is expressed as the integral of the source, Green's function, and contrast function, which forms our forward model. To solve this problem, we employ an iterative method that utilizes the Born approximation at each step. During the kth iteration of this method, the total field ATOC-1 is computed for the contrast function K-1 obtained in the previous iteration, using the state equation. By substituting ATOC-1 into the data equation and applying the Tikhonov regularization method, the optimization problem is solved to obtain K. For the first iteration, Chi0 is chosen arbitrarily. The slide presents the formulation associated with this solution, including the closed-form solution. The scattering model G, which is typically nonlinear due to the multiple scattering interactions, makes traditional iterative approaches computationally expensive and time-consuming. Traditional methods, such as the Born iterative method and contrast source inversion, require iterative optimization with heavy computational cost. Due to the time-consuming nature of these iterative methods, we need faster techniques. With advancements in deep learning, particularly convolutional neural networks, CNNs, we have the potential to solve inverse scattering problems in real time, offering faster reconstructions without sacrificing accuracy. CNNs learn a mapping epsilon hat equals GS where epsilon hat is the predicted permittivity from the scattering data. CNNs are well suited to handle the spatial complexities of EM scattering, bypassing some of the challenges associated with conventional iterative techniques and provide real-time solutions. This approach is particularly promising for achieving real-time imaging solutions. In more details point of view, the CNN combination with UNet architecture can be divided to different training schemes for solving inverse scattering problems. One of them is direct inversion. This scheme uses CNN to directly map scattering data to the permittivity distribution without integrating additional physics constraints or models. 2. Backpropagation, a more conventional approach where the neural network learns through optimization using backpropagation. In this scheme, CNN training is performed using backpropagation with physics-informed loss functions, which may include Tikhonov regularization, improving the inversion process by penalizing unrealistic solutions. 3. Dominant current scheme, DCS emphasizes the dominant current contributions in the inversion process. The dominant current ID can be obtained by singular value decomposition, SVD, of the forward model matrix G. This approach allows for faster and more accurate computations. In addition, a key aspect of the artificial intelligence-based approach is how physics is incorporated into the ML models. 3 strategies are highlighted as shown in the right side of the slide. 1. Learning after physics processing. In this approach, physics-based models are used to pre-process the input data for ML models, ensuring that the data passed to the neural network is physically meaningful, which can guide the model toward more accurate solutions. Here, the data pre-processing involves applying a physics-based model to obtain an initial estimate of epsilon. This pre-processing helps to set a physically meaningful input for the ML model. 2. Learning with physics loss. Here, physics knowledge is embedded directly into the loss function of the neural network. This might involve adding regularization terms or physical constraints, such as Tikhonov regularization, to guide the network in producing physically consistent solutions. The Tikhonov regularization technique plays a vital role in stabilizing the inversion process by adding a penalty for overly complex solutions, thus ensuring the smoothness of the reconstructed permittivity profile. This regularization is crucial for mitigating the ill-posed nature of inverse problems and preventing overfitting, especially when dealing with noisy or incomplete data. 3. Learning with physics models. The final approach uses physics-based insights to shape the architecture of the ML model itself, ensuring that the network structure respects known physical laws and relationships, which improves the model's ability to generalize and produce meaningful predictions. For instance, the network might be designed to inherently respect conservation laws or other physical principles, optimizing the structure to align with these constraints. Combining deep learning with physics-informed ML methods offers a promising approach to inverse EM problems. This integration facilitates rapid and accurate solutions, significantly reducing computation times compared to traditional methods. The potential applications are extensive, including medical diagnostics, geophysical exploration, and non-destructive testing, where real-time quantitative imaging is crucial. The synergy between advanced deep learning techniques and physics-based insights represents a major step forward in addressing the computational challenges associated with conventional iterative algorithms. The direct inversion method in AI-powered electromagnetic imaging represents a promising approach to solving the complex inverse electromagnetic scattering problem in brain imaging. The core objective of this method is to reconstruct the internal properties of the brain, particularly the permittivity profile, a measure of how the brain tissue interacts with electromagnetic waves, by analyzing the scattered electromagnetic fields that result from incident waves passing through the brain. The inverse scattering problem is inherently difficult due to its ill-posed and nonlinear nature. This means that small changes in the scattered wave data can lead to large uncertainties in the reconstructed brain images, making traditional mathematical approaches less effective. The direct inversion scheme in AI-powered electromagnetic imaging presents a promising solution for the inverse scattering problem in brain imaging. It offers a fast, direct approach for reconstructing brain structures from scattered electromagnetic fields using deep learning, with the potential for real-time medical imaging. However, for more complex cases, complementary or more sophisticated techniques may be required to enhance accuracy and precision. However, the integration of AI-powered solutions like deep learning offers a more robust and reliable alternative to this challenge. Before diving into the inverse problem, it is essential to understand the forward scattering problem, which involves solving the electric field integral equation, EFIE. This equation describes how incident electromagnetic waves interact with the brain tissue, producing scattered fields. These scattered fields are measured by antennas or sensors positioned around the head. The forward problem assumes that the internal properties, such as permittivity, of the brain are known, and the task is to predict how waves will scatter. Numerical methods like the method of moments, MOM, finite element method, FEM, and finite difference time domain, FDTD, are commonly used to simulate the forward scattering problem. In addition, this analysis can be done by electromagnetic wave software like CST Studio, HFSS, and FICO. These simulations generate scattering parameters, S parameters, which represent how electromagnetic waves scatter based on the material properties of the brain. This data is essential for creating a comprehensive training set for the AI model. By this way, we can generate databases to train the AI-based model, such as convolutional neural network, CNN. CNN has been trained on a large dataset that links known permittivity distributions with their corresponding scattered fields. During the training phase, the network learns the intricate relationships between the scattered field measurements and the underlying internal properties of the brain. The direct inversion scheme offers a fast and simplistic approach to solving the inverse scattering problem by employing a convolutional neural network, CNN, to directly map the scattered fields to the internal brain structures. The inverse scattering problem flips the process. Instead of predicting how waves scatter from known internal properties, the goal is to reconstruct the unknown internal properties of the brain, specifically, the permittivity profile, from the scattered wave data. In the context of brain imaging, this is particularly challenging due to the complex nature of brain tissue and the nonlinearity of the problem. The scattered wave data alone is insufficient to reconstruct accurate images, without sophisticated algorithms capable of dealing with these complexities. In this scheme, the scattered electromagnetic fields, captured as S parameters by the sensor array around the head, are directly input into a pre-trained CNN. CNN processes the input data by passing it through multiple convolutional layers, where the network automatically learns to detect patterns and features in the scattered field data that correspond to different permittivity profiles. The final output of the network is a reconstructed image that represents the internal permittivity distribution of the brain. This approach bypasses the need for traditional iterative algorithms that often struggle with nonlinearity and noise in the data, allowing for a more real-time or near-instantaneous reconstruction of the brain's internal structures. While the direct inversion scheme, DIS, is computationally efficient and fast, it does have limitations in terms of accuracy, especially when dealing with complex or highly nonlinear profiles. The model's effectiveness relies heavily on the quality and diversity of the training data, as well as the network's ability to generalize from this data to unseen cases. For simple or linear scattering environments, DIS can provide acceptable results. However, for more complicated scenarios, such as those involving strong scatterers or intricate structures within the brain, the method may struggle to achieve the desired accuracy. Since the convolutional neural network, CNN, directly maps the input data, scattered electromagnetic fields, to the output, permittivity profiles, there is no need for the iterative, computationally intensive processes often required in solving inverse problems. This makes direct inversion scheme, DIS, particularly valuable for real-time applications, such as emergency brain imaging during critical medical events like strokes, where rapid diagnosis is crucial. However, the simplicity of DIS also presents challenges. The nonlinear nature of the inverse scattering problem means that basic direct inversion might struggle to accurately capture the intricate details within the brain, especially in complex scattering environments or when dealing with heterogeneous tissue structures. In this slide, we introduce some advanced techniques to enhance the performance of DIS. Specifically, we focus on the backpropagation scheme, BPS, which is highlighted on the left side of the slide. BPS improves accuracy and robustness by incorporating additional steps, either before or after the CNN processes the data. This helps overcome the limitations of straightforward direct inversion. Although it is possible to train a CNN to directly regress from the measured scattered fields E_s to relative permittivity epsilon r, the learning process can be simplified by first performing non-iterative inversion algorithms before training. BPS is one such method based on CNNs, designed to address the inverse scattering problem with enhanced precision. The key idea behind BPS is that the induced current IB in the scattering medium is proportional to the backpropagated field, which is highly effective for reconstructing weak scattering objects. The mathematical representation of this process is demonstrated in each step. The BPS workflow improves the reconstruction of permittivity profiles by considering the interaction between the induced current and total field, particularly for weak scattering objects. By combining the information from all incident fields, the least squares solution is computed for each element of the contrast. This refined contrast information is then fed into the CNN as the input, while the outputs are the true contrasts for the domain. BPS is applicable for arbitrary incidence fields and is effective for both near and far field measurements, setting it apart from traditional methods like filtered backpropagation, FBP, in diffraction tomography. It's essential to distinguish the backpropagation in BPS from the error backpropagation algorithm used in CNNs for updating weights. The backpropagation in BPS refers to the physical propagation of electromagnetic fields, whereas in CNNs, it refers to the computational process of optimizing the network. BPS enhances the accuracy of inverse scattering solutions, especially for complex media, by using an intermediate backpropagation step before feeding the data into the CNN. This makes it a robust method for reconstructing fine details in medical imaging applications, like brain scans, where time and precision are both critical. In addition, on the right side, we can see the data preprocessing structure, which plays a crucial role in preparing the original FDTD signal data for the deep learning model. This section ensures that the raw data generated by the FDTD solver, consisting of time-domain electromagnetic signals, is correctly transformed into a format that the neural network can process efficiently. The data preprocessing phase takes the original signal map and applies steps such as downsampling and normalization to compress and standardize the data. This step is critical because it bridges the gap between the complex FDTD simulations and the deep learning phase, ensuring that the data is efficiently utilized for training. Following this is the post-processing structure, where we aim to further improve the imaging performance of the FCERNN using UNet, an image optimization module. UNet, a well-known deep learning architecture for biomedical image segmentation, is employed here for refining the results generated by the 3D FCERN. The UNet architecture, with its downsampling and upsampling components, processes the 2D slices of the brain reconstruction results from the FCERNN and produces the final inversion results with improved resolution and accuracy. The downsampling part extracts both global and local features from the images using convolutional and pooling layers, while the upsampling part restores the segmented maps back to their original size, ensuring uniform color difference and feature preservation. Additionally, the skip concatenate connections between corresponding layers in the downsampling and upsampling parts allow for better feature reuse, thereby enhancing the model's ability to produce more accurate and detailed reconstructions of the brain tissue. In essence, this slide presents a complete picture of the data processing workflow, starting from raw signal preprocessing, moving through deep learning-based reconstruction, and ending with UNet-based post-processing for final optimized imaging results. PINs represent a novel approach to solving inverse problems by incorporating physical laws directly into the structure of a neural network. This hybrid framework allows the neural network to respect the constraints imposed by the underlying physics, improving accuracy and reducing the need for large amounts of training data. In inverse EM problems like microwave brain imaging, the PDEs governing Maxwell's equations form the basis for how electromagnetic fields interact with different materials, e.g., brain tissue, blood. These equations can be solved using a variety of discretization schemes like the finite difference method, FDM, finite element method, FEM, or spectral methods, SM. The discretization schemes transform continuous PDEs into a form that can be handled by the network, making them applicable to domains like the head where complex structures and geometries exist. The slide illustrates this transformation, where the integral and differential equations are applied to real-world problems using these discretization techniques. Simultaneously, automatic differentiation (AD) allows the PINN to compute derivatives of complex quantities directly, improving the network's ability to backpropagate gradients during training. This combination of discrete and analytical methods is critical for solving inverse EM problems, where one must infer the unknown permittivity and conductivity profiles inside the brain from observed scattered fields. The flowchart illustrating forward and backward propagation shows how pins process input data through a neural network in stages, first predicting intermediate quantities such as scattered fields and contrast sources, forward pass, and then using backpropagation to adjust the model parameters based on error calculations, backward pass. The forward step predicts physical quantities, e.g., electric fields, while the backward pass uses error gradients to adjust the network to better match the measured data. For instance, in microwave brain imaging, the forward process computes how microwaves scatter when interacting with brain tissue, while the backward pass uses this information to refine the model's internal parameters, permittivity and conductivity values. In pins, the loss function incorporates not only traditional data-driven loss, i.e., how well the network's output matches the observed data, but also physics-based losses derived from the governing PDEs. This dual approach ensures that the model respects physical laws while also fitting the experimental data. The loss function combines the mean squared error, MSE, between predicted fields and measured data with the MSE of the governing PDEs, allowing the model to optimize both aspects simultaneously. The total loss is minimized using optimization algorithms, leading to improved model accuracy and stability, especially in inverse problems where data might be scarce or noisy. This slide highlights how physics-informed neural networks are applied to the inverse electromagnetic scattering problem in microwave brain imaging, addressing the process through three key stages: integral, differential, and simultaneous methods. This slide emphasizes the roles of the integral, differential, and simultaneous methods in the PINN framework for microwave brain imaging, and how they contribute to the overall process of real-time brain image reconstruction. The key idea here is the simultaneous use of forward and inverse processes within the neural network. The integral formulation, top left equation, captures how the brain's material properties, such as permittivity, affect the electromagnetic fields in the forward process. The equation represents the total electric field, E, as a combination of the incident field and the scattered field, which is integrated over the entire volume of the brain. The forward process uses this integral approach to predict how microwaves interact with the brain tissues, resulting in scattered fields detectable by external sensors. The neural network computes the contrast source, J, and the electric field, E, based on an initial guess for the brain's permittivity. These predictions guide the model in simulating the interaction between microwaves and the complex anatomy of brain tissues. The differential formulation, top right equation, is essential for capturing the local variations in electric and magnetic fields within the brain, governed by Maxwell's equations. The differential equations describe how the electric field, Ez, and magnetic fields, Hx, high, evolve over time and space, accounting for the influence of permittivity and permeability in the brain tissues. This method is crucial for simulating the intricate dynamics of electromagnetic wave propagation through different types of brain tissue, white matter, gray matter, cerebrospinal fluid, etc. The recurrent neural network, RNN, uses these differential equations to calculate the fields at each time step, employing finite differences to approximate the partial derivatives, which ensures that the evolving wavefronts and field interactions are accurately simulated. The simultaneous method, illustrated in the lower diagrams, integrates both forward and inverse processes within the neural network to refine the brain model iteratively. The forward process, shown in green, calculates the wave propagation based on an initial estimate of the brain's properties, while the inverse process, in blue, works to update the permittivity by using measured scattered field data. This dual process framework ensures that the neural network progressively improves its understanding of the brain's internal material properties, such as permittivity, by comparing predicted and actual measured data in real time. This simultaneous approach, where both forward and inverse processes are interwoven, allows the network to unroll over time, learning how electromagnetic waves scatter and propagate through the brain while continuously refining the model. Each time step in the forward process corresponds to the wave propagation, and the inverse process updates the brain's permittivity by minimizing the difference between the measured and predicted scattered fields. This method enhances the accuracy of the reconstructed image of the brain's internal structures. The final output of the neural network is a reconstructed image of the brain's permittivity distribution, which provides critical insights into the brain state, such as identifying whether a stroke has caused ischemia, blockage, or hemorrhage, bleeding. By embedding Maxwell's equations directly into the network, PINs provide a robust framework for solving inverse EM problems like microwave brain imaging. The combination of integral, differential, and simultaneous methods within the neural network allows for real-time brain imaging, a breakthrough that can lead to portable, non-invasive imaging systems deployable in emergency rooms or ambulances. These advancements can drastically improve stroke diagnostics by providing fast, accurate, and actionable insights into brain conditions. In this slide, to demonstrate the effectiveness of the deep learning for inverse electromagnetic scattering problems, we put the reconstructed image results from the different papers that cited in the references sections. On this slide, we explore the reconstruction of 3D relative permittivity and conductivity distributions in the human brain using the FCRNN model, along with its enhanced version incorporating UNet. Starting with the left side, we see how the FCRNN model performs the core task of reconstructing both permittivity and conductivity maps. Notice how the 3D structures and 2D slices reflect an accurate representation of the brain's internal tissues, which are compared here to the ground truth. The FCRNN is particularly effective at capturing the overall shape and structure of brain tissues. One of the key advantages of FCRNN is its speed and efficiency. By using a fully convolutional architecture, the model significantly reduces computational complexity, making it ideal for real-time applications. It is also capable of handling high-resolution, high-contrast objects, which is essential in medical imaging of complex structures like the brain. Furthermore, its scalability allows it to manage large domains, such as the full human brain. However, the FCRNN model isn't without limitations. While it reconstructs the general structure quite well, there are some notable inaccuracies along the tissue boundaries. You'll also notice some artifacts and noise, especially in environments with lower signal-to-noise ratios. As we reduce the SNR, these inaccuracies become more pronounced, leading to blurring and misrepresentation of finer tissue details. Now, moving to the right side, we introduce UNet, which plays a significant role in enhancing the results. When combined with FCRNN, UNet focuses on refining the edges of the tissues and eliminating the noise, which greatly improves the clarity and accuracy of the images. Let's look at how UNet enhances performance under varying SNR conditions. At SNR equals 10 dB, where the FCRNN results are visibly noisy and blurred, UNet steps in and cleans up the noise while sharpening tissue boundaries. Even in these challenging conditions, the enhanced model is able to recover critical details that would otherwise be lost. At higher SNRs, like 20 dB and 30 dB, the combined model produces robust, high-quality reconstructions that closely resemble the ground truth, effectively restoring the small but important structures within the brain. In summary, while FCRNN offers fast and scalable reconstructions, it faces challenges with boundary noise and sensitivity to low SNR environments. This is where the inclusion of UNet comes into play, addressing these limitations and providing a more refined and accurate output, particularly in noisy conditions. Together, FCRN and UNet form a powerful solution for real-time electromagnetic brain imaging, offering the potential for high-quality, reliable imaging even under difficult conditions.